Right now, at this very moment, you are hurtling through space at 828,000 kilometers per hour. You can't feel it. You're sitting still, lying down, perfectly at rest. But Earth is spinning, and Earth is orbiting the Sun. And the Sun is dragging the entire solar system around the galaxy at nearly 1,000,000 kilometers per hour. You've traveled thousands of kilometers just since you started reading this sentence, and you didn't feel a thing. But here's what makes it stranger. Despite this incredible speed, it takes us 230 million years to complete just one orbit around the Milky Way. We call that a galactic year. And in all of human history, every empire that has risen and fallen, every civilization, every story ever told, we haven't even completed 1/10 of a single galactic orbit. The last time we were in this part of the galaxy, dinosaurs hadn't even appeared yet. Tonight, you're going to discover that the solar system is far stranger than the tidy diagrams we learned in school. There are planets that rain diamonds, moons with underground oceans larger than all of Earth's seas combined, a storm on Jupiter that has been raging for over 350 years, and two spacecraft that have left the solar system entirely, carrying golden records with the sounds of Earth into the void between stars. But perhaps most surprising of all, almost everything you're about to hear is something scientists discovered in your lifetime, or your parents' lifetime, or your grandparents'. We're living in the golden age of solar system exploration, and each year brings revelations that rewrite what we thought we knew. Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Maybe you've had a long day, or perhaps you're someone who finds comfort in cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. Let your breathing slow, your shoulders soften, your thoughts settle like dust on a quiet moon. Because tonight, we're drifting through the solar system, discovering 100 facts that will surprise you, soothe you, and maybe change the way you see the night sky forever. And just before we begin, if these explorations help you unwind or spark your curiosity, consider subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The solar system began as a cloud. About 4.6 billion years ago, a vast nebula of gas and dust began to collapse. Something triggered it. Perhaps shock waves from a nearby supernova sent ripples through space. Whatever the cause, gravity took over. The cloud spun faster as it contracted, flattening into a disk. At its center, material piled up, heating and compressing until nuclear fusion ignited. The Sun was born. Here's the first surprise. The Sun contains 99.86% of all the mass in the solar system. Jupiter, Saturn, Earth, Mars, every asteroid, comet, and grain of dust combined. All of it amounts to less than 0.2%. The Sun's mass is 330,000 times that of Earth. Its volume could contain 1.3 million Earths. It's not the largest star in existence, not even close. But to the worlds that orbit it, the Sun is everything. At its core, temperatures reach 15 million degrees Celsius. Here, every second, the Sun fuses about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons become pure energy, radiating outward. But here's what's strange. This energy doesn't escape quickly. It can take over 1,000,000 years for a single photon to travel from the core to the surface, bouncing through dense plasma, absorbed and re-emitted countless times. The sunlight warming your face right now began its journey before modern humans existed. The Sun's surface, the photosphere, sits at about 5,500 degrees Celsius. Then, something counterintuitive happens. Above the surface, the corona, the Sun's outer atmosphere, suddenly spikes to over 1 million degrees. Scientists are still piecing together why the corona is so much hotter than the surface below. Current evidence suggests magnetic fields and wave heating play a role, though the complete picture remains elusive. The sun doesn't rotate as a solid body. At the equator, it completes one rotation in about 25 days. Near the poles, closer to 36 days. Over time, this differential rotation twists the sun's magnetic field into complex knots and loops, creating sunspots, solar flares, and coronal mass ejections. These events follow an 11-year cycle. During solar maximum, the surface erupts with activity. During solar minimum, it quiets. But even during quiet periods, the sun is never truly still. Solar flares release as much energy as billions of nuclear bombs in mere minutes. Coronal mass ejections hurl billions of tons of plasma into space at speeds exceeding 3 million miles per hour. When these ejections reach Earth, they interact with our magnetic field, compressing it and triggering auroras, those shimmering curtains of green, purple, and red light that dance near the poles. The sun also exhales constantly, sending out a stream of charged particles called the solar wind. This wind flows outward at about 400 kilometers per second, carrying the sun's magnetic field with it and creating a vast protective bubble called the heliosphere. At the edge of this bubble, roughly 120 astronomical units away, the solar wind finally slows and meets the interstellar medium. Only 2 spacecraft have ever crossed this boundary. Light from the sun takes just over 8 minutes to reach Earth. The sunlight you see is from 8 minutes ago. It reaches Mars in about 13 minutes, Jupiter in 43 minutes, and takes over 4 hours to touch Neptune. Even traveling at the fastest speed in the universe, light still takes time to cross the solar system's vast distances. The sun is middle-aged, about halfway through its 10 billion year lifespan. In another 5 billion years, it will exhaust the hydrogen in its core and swell into a red giant, possibly engulfing Mercury, Venus, and Earth. After shedding its outer layers, it will leave behind a white dwarf, a dense, hot core slowly cooling over trillions of years. But for now, it burns steadily, an ordinary star in an ordinary phase, quietly holding everything together with its gravity. The inner solar system is a realm of extremes. Here, 4 small, dense worlds orbit close to the Sun: Mercury, Venus, Earth, and Mars. They're called terrestrial planets because they have solid surfaces you could theoretically stand on, though on most of them, you wouldn't survive long enough to take a single step. These worlds formed in the scorching inner disk of the early solar nebula, where temperatures were too high for water ice or other volatile compounds to solidify. Only materials with high melting points, metals like iron, and rocks like silicates, could survive here. This is why the inner planets are small and dense, built from the heaviest materials available. Mercury, the closest planet to the Sun, holds a record most people don't know about. It has the most extreme temperature swings in the solar system. During its day, which lasts 59 Earth days, surface temperatures soar to 430 degrees Celsius, hot enough to melt lead. But Mercury has almost no atmosphere to trap heat, so when night falls, temperatures plummet to minus 180 degrees Celsius. That's a swing of over 600 degrees. Mercury is only slightly larger than Earth's moon, making it the smallest planet. But here's the twist: it's unusually heavy. Mercury's iron core makes up about 60% of its entire mass, far more than any other planet. Scientists believe a massive impact early in its history may have stripped away much of its rocky outer layers, leaving behind this dense, metal-rich world. Mercury's orbit creates another oddity. It completes 3 rotations on its axis for every 2 orbits around the Sun, a 3.2 spin orbit resonance. This means a single day on Mercury lasts 59 Earth days. while a year takes only 88 Earth days. In other words, a year on Mercury is shorter than a day. Venus, the second planet, is often called Earth's twin because of its similar size and mass. But calling Venus Earth's twin is like calling a blast furnace a cozy fireplace. Venus is hell. Its surface temperature hovers around 465 degrees Celsius, hotter than Mercury, despite being farther from the Sun. This is caused by a runaway greenhouse effect. Venus's thick atmosphere, composed of 96% carbon dioxide, traps heat so effectively that the entire planet glows with infrared radiation. The atmospheric pressure on Venus's surface is 90 times that of Earth's, equivalent to being a kilometer underwater. The air is so dense, it behaves almost like a fluid. And if that weren't enough, the clouds are made of sulfuric acid. These clouds are so reflective that Venus is the brightest planet in our sky, visible even during daylight if you know where to look. Venus also rotates backward compared to most planets, and extremely slowly. A day on Venus lasts 243 Earth days, longer than its year of 225 Earth days. This means that if you could stand on Venus's surface, which you absolutely could not, the sun would rise in the west, set in the east, and take longer to complete one sunrise to sunrise cycle than it takes Venus to orbit the sun entirely. Earth, the third planet, is the only world known to support life. But what makes Earth special isn't just the presence of water or oxygen, it's timing and luck. Earth sits in the habitable zone, where temperatures allow liquid water to exist on the surface. It has a magnetic field generated by its molten iron core, protecting the atmosphere from being stripped away by solar wind. And it has the moon. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized object called Theia collided with our planet. The impact was so violent it melted both bodies and ejected massive amounts of debris into orbit. This debris, over the course of about a year, coalesced to form the Moon. The Moon stabilizes Earth's axial tilt, preventing wild climate swings, and creates tides that have shaped life's evolution. Without that ancient, catastrophic collision, Earth as we know it, and quite possibly life itself, might not exist. Mars, the fourth planet, is a cold, desert world that once looked very different. Ancient river valleys, lake beds, and minerals that only form in liquid water paint a picture of a warmer, wetter past. Based on these geological clues, scientists infer that Mars had a thicker atmosphere and flowing water on its surface billions of years ago. But without a strong magnetic field to protect it, the solar wind gradually stripped away most of its atmosphere, leaving behind the thin, cold world we see today. Mars is about half Earth's size, with a day that lasts 24 hours and 37 minutes. It has the largest volcano in the solar system, Olympus, Mons, standing about 22 kilometers high, nearly 3 times taller than Mount Everest. It also has Valles Marineris, a canyon system stretching over 4,000 kilometers and reaching depths of 7 kilometers. If placed on Earth, it would span the entire United States. Mars has 2 tiny moons, Phobos and Deimos, thought to be captured asteroids. Phobos orbits so close to Mars that tidal forces are pulling it inward. In about 50 million years, it will either crash into the planet or break apart to form a ring. Mars, the planet we once dreamed of terraforming, may one day have rings like Saturn. The inner rocky worlds may be small, but they are rich in diversity. Scorched, shrouded, teeming with life, and frozen in memory of what once was. Between the orbits of Mars and Jupiter lies a vast ring of rocky debris known as the asteroid belt. It's often depicted in science fiction as a dense, chaotic field of spinning rocks, but in reality, the asteroids are spread out over an enormous volume of space. If you were to travel through the asteroid belt, you would likely see nothing but empty space, with the occasional faint speck of light in the distance. There are millions of asteroids in the belt, ranging from tiny pebbles to objects hundreds of kilometers across, but the total mass of all asteroids combined is less than 4% of the Moon's mass. The largest object in the asteroid belt is Ceres, a dwarf planet about 940 kilometers in diameter. Ceres is round, shaped by its own gravity, and contains a significant amount of water ice beneath its surface. Recent missions have detected bright spots on Ceres' surface, thought to be deposits of salt left behind when subsurface ice sublimated and brought minerals to the surface. Ceres may even have a subsurface ocean, kept liquid by residual heat from its formation. Vesta, the second largest object in the belt, is about 425 kilometers across. Unlike Ceres, Vesta has a rocky, differentiated interior with a crust, mantle, and core, much like the terrestrial planets. It also has a massive impact crater near its south pole, so large it exposed layers of the asteroid's interior. Some of the meteorites that fall to Earth are fragments of Vesta, blasted into space by ancient collisions. Most asteroids in the belt are remnants of the early solar system. When the planets were forming, Jupiter's immense gravity stirred up the region between Mars and itself, preventing the material there from coalescing into a single planet. Instead, the rocks remained scattered, colliding, and fragmenting over billions of years. Some asteroids are primitive, unchanged since the solar system's formation. They contain organic compounds and water-bearing minerals, offering clues about the ingredients that built the planets. Not all asteroids stay in the belt. Some have orbits that bring them closer to the Sun, crossing the paths of the inner planets. These are called near-Earth asteroids, and thousands have been cataloged. Some pass, within a few million kilometers of Earth, uncomfortably close on cosmic scales. A few even pose a potential impact threat. Scientists monitor these objects closely and are developing methods to deflect them if necessary. In 2022, NASA's DART mission successfully demonstrated that a spacecraft could change an asteroid's trajectory by colliding with it. The asteroid belt also contains families of asteroids that share similar orbits and compositions. These families are thought to be the fragments of larger asteroids that were shattered in collisions. By studying these families, astronomers can piece together the violent history of the asteroid belt and learn how impacts have shaped the solar system over time. Some asteroids even have their own moons. Ida, a small asteroid in the belt, has a tiny moon named Dactyl, only about 1.5 kilometers across. Before this discovery in 1993, scientists didn't know asteroids could have satellites. Since then, dozens of binary asteroids have been found, some with multiple moons. These systems offer insights into how objects interact gravitationally on small scales. The asteroid belt is not a wasteland. It's a museum of the solar system's early history, a graveyard of failed planets, and a resource-rich frontier. Some asteroids contain valuable metals like platinum and gold. In the future, mining asteroids could provide materials for building spacecraft and habitats in space, reducing the need to launch heavy payloads from Earth's deep gravity well. For now, the belt drifts silently between the rocky and giant worlds, a reminder that planets are not the only inhabitants of the solar system. Beyond the asteroid belt, the solar system transforms. Here, where sunlight weakens and temperatures plummet, the giant planets reign, massive spheres of gas and liquid swirling around cores of rock and ice. They gathered not just rock and metal, but enormous amounts of hydrogen and helium, becoming colossal worlds that dwarf everything in the inner solar system. Jupiter is the undisputed king. Its mass is more than twice that of all the other planets combined. Over 1,000 Earths could fit inside its volume. Yet despite its enormous size, Jupiter spins faster than any other planet. One full rotation takes less than 10 hours. This rapid spinning creates winds that race across the surface at over 400 kilometers per hour, organizing the clouds into colorful bands of reds, browns, whites, and yellows. The Great Red Spot, Jupiter's most famous feature, is a storm larger than Earth that has been raging for over 350 years. Think about that. The storm has been spinning continuously since before the American Revolution, and it shows no signs of stopping. Recent observations reveal it's been shrinking, though no one knows if it will eventually fade or regain its size. Jupiter has no solid surface. If you tried to descend into it, you would first pass through the upper atmosphere of hydrogen and helium. As pressure increased, the gas would become denser, eventually transitioning into liquid hydrogen. Deeper still, under crushing pressure, hydrogen would become metallic, conducting electricity like a metal. At the very center, there may be a dense core of rock and ice, but we can't be certain. Jupiter guards its interior secrets well. Jupiter has at least 95 known moons, and astronomers continue discovering more. The 4 largest were discovered by Galileo in 1610 and are called the Galilean moons: Io, Europa, Ganymede, and Callisto. Each is a world unto itself. Io is the most volcanically active body in the solar system, constantly reshaped by eruptions of sulfur and molten rock. Europa hides a global ocean beneath its ice, potentially twice as much water as all of Earth's oceans. Ganymede is the largest moon in the solar system, bigger than Mercury, and the only moon with its own magnetic field. Callisto is ancient and heavily cratered, its surface largely unchanged for billions of years. Saturn, the 6th planet, is perhaps the most beautiful. It's less massive than Jupiter, but larger in volume, with a density so low it would float in water, if you could find an ocean big enough. Like Jupiter, it spins quickly, completing one rotation in just over 10 hours, giving it a pronounced bulge at the equator. But Saturn's true glory is its rings. They extend hundreds of thousands of kilometers from the planet, yet are remarkably thin, in some places only tens of meters thick. The rings are made of countless particles of ice and rock, ranging from tiny grains to boulders the size of houses. Each particle orbits Saturn independently, creating intricate patterns, waves, and gaps shaped by the gravitational influence of Saturn's moons. Here's something that might surprise you. Saturn's rings may be relatively young. Some research suggests they could have formed just a few 100 million years ago, meaning that when dinosaurs walked the Earth, Saturn might have been ringless. The rings could be the remnants of a moon torn apart by tidal forces, though this remains an area of active investigation. Saturn has at least 146 officially confirmed moons, but that number keeps growing. In March 2025, astronomers announced the discovery of 128 additional tiny moons, bringing the total to 274 confirmed satellites, more moons than any other planet. The largest, Titan, is bigger than Mercury and is the only moon in the solar system with a thick atmosphere. Titan's atmosphere is so dense and its gravity so low that if you stood on its surface wearing only a pressure suit and an oxygen mask, you could strap on wings and fly. Saturn also has something utterly bizarre at its north pole: a massive hexagonal storm. The hexagon is a jet stream with sides about 13,800 kilometers long, wider than Earth. It's been observed for decades, persisting through seasonal changes, and no one fully understands why it maintains this perfect six-sided shape. The pattern appears to emerge from Saturn's rotation and atmospheric dynamics, but the exact mechanism remains one of the solar system's beautiful mysteries. Jupiter and Saturn, the gas giants, are worlds of extremes and elegance: massive, fast-spinning, ringed, and full of moons. They are the solar system's architects, their gravity shaping the orbits of everything around them. As of 2025, astronomers have confirmed over 891 moons orbiting planets, dwarf planets, and even asteroids throughout the solar system. These moons range from tiny, irregularly shaped rocks to worlds larger than Mercury. Some are geologically dead, frozen in time. Others are active, dynamic, and may harbor the ingredients for life. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Over 400 active volcanoes dot its surface, constantly erupting molten sulfur and silicate rock. Some lava fountains shoot hundreds of kilometers into space. Io's volcanic fury isn't powered by internal radioactives, decay like Earth's volcanism. It comes from tidal heating. Jupiter's immense gravity, combined with the gravitational tugs from neighboring moons Europa and Ganymede, flexes Io's interior like a stress ball, generating tremendous heat. The surface is painted in yellows, oranges, and reds from sulfur compounds deposited by endless eruptions. Europa may be the most promising place to find life beyond Earth. Beneath its icy crust lies a global ocean of liquid water, possibly twice the volume of all Earth's oceans combined. The ice shell is fractured with cracks, ridges, and chaotic terrain, evidence of the ocean below shifting and reshaping the surface. Tidal heating keeps the ocean liquid. If hydrothermal vents exist on Europa's ocean floor, they could provide energy and nutrients similar to ecosystems in Earth's deepest oceans, where life thrives in total darkness. In 2024, NASA launched the Europa Clipper mission, which will arrive in the 2030s to study this enigmatic moon in detail. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It's the only moon with its own magnetic field, generated by a liquid iron core. Beneath its icy cratered surface, there may be a subsurface ocean sandwiched between layers of ice. Ganymede is a complex, layered world that challenges our understanding of what a moon can be. Saturn's moon Titan is perhaps the strangest. It's the only moon with a thick atmosphere, denser than Earth's. The atmosphere is mostly nitrogen, with clouds of methane and ethane. On Titan's surface, liquid methane and ethane flow in rivers and fill vast lakes and seas. The largest, Kraken Mare, is larger than the Caspian Sea. Surface temperatures hover around minus 180 degrees Celsius, so cold that water ice behaves like bedrock. In 2005, the Huygens probe descended through Titan's atmosphere and landed on its surface, sending back images of rounded pebbles made of water ice and dark terrain possibly covered in liquid. Methane. Titan's chemistry is incredibly complex, with organic molecules forming in the upper atmosphere and raining down onto the surface. Some scientists speculate that Titan could support life based on liquid methane instead of water, a biochemistry entirely alien to anything on Earth. Enceladus, another of Saturn's moons, is small but astonishingly active. Geysers near its south pole shoot water vapor, ice particles, and organic molecules hundreds of kilometers into space. These geysers feed Saturn's E-ring. Beneath the ice lies a global ocean, and the discovery of organic molecules in the geyser plumes has made Enceladus one of the top targets in the search for life. Triton, Neptune's largest moon, is unusual for many reasons. It orbits backward, suggesting it was captured from the Kuiper Belt rather than formed with Neptune. It has nitrogen geysers that create dark streaks on its surface, and its orbit is slowly decaying. In a few billion years, Triton will either crash into Neptune or be torn apart to form rings. Earth's moon, though familiar, is also remarkable. It's unusually large relative to its parent planet, likely formed from debris after a Mars-sized object collided with Earth 4.5 billion years ago. The moon stabilizes Earth's axial tilt, regulates our climate, creates ocean tides, and is the only celestial body humans have walked on. Moons are not just satellites. They are worlds, diverse and dynamic, shaped by gravity, heat, impacts, and time. Some may harbor life. Others preserve records of the solar system's violent past. In their variety, they remind us that wonder exists at every scale. Farther still from the sun lie the ice giants, Uranus and Neptune. These worlds are fundamentally different from Jupiter and Saturn. While they still contain hydrogen and helium, they're dominated by heavier materials, water, methane, and ammonia, that exist in strange, high-pressure states deep within. These substances behave less like ice and more like hot, dense fluids conducting heat and electricity. Uranus and Neptune are smaller than the gas giants, but still enormous compared to Earth. Uranus is one of the strangest planets in the solar system, and here's why. It rotates on its side. Its axial tilt is 98 degrees, meaning one of its poles points almost directly at the Sun. This likely resulted from a massive collision early in its history, an impact so violent it knocked the entire planet sideways. Because of this extreme tilt, Uranus experiences the most unusual seasons imaginable. For 42 Earth years, one pole basks in continuous sunlight, while the other sits in total darkness. Then, for the next 42 years, the situation reverses. It takes Uranus 84 Earth years to complete one orbit around the Sun. Imagine spending your entire childhood in permanent daylight, only to enter adulthood as perpetual night begins. Uranus appears as a pale blue-green disk, colored by methane in its upper atmosphere that absorbs red light and reflects blue and green wavelengths. For decades after Voyager 2's flyby in 1986, scientists thought Uranus was a featureless, boring world. But recent observations with advanced telescopes have revealed storms, clouds, and atmospheric dynamics that were invisible to earlier instruments. Uranus is more active than it first appeared. We simply weren't looking closely enough. Uranus has at least 27 known moons, all named after characters from Shakespeare and Alexander Pope. The only planet whose moons aren't named after mythological figures. The largest moon, Miranda, has one of the most bizarre surfaces in the solar system: towering cliffs, chaotic terrain, and features that suggest the moon may have been shattered by an impact and reassembled by its own gravity. Neptune, the eighth and most distant planet, is a world of supersonic winds and vivid blue coloring. Like Uranus, its color comes from methane, but Neptune's deeper, more saturated blue suggests something else is at play, possibly an unknown compound in its atmosphere. Neptune orbits at an average distance of 4.5 billion kilometers from the Sun, taking 165 Earth years to complete one orbit. Since its discovery in 1846, Neptune has completed less than 2 full orbits. Here's what makes Neptune remarkable. It has the fastest winds in the solar system. Winds in Neptune's atmosphere reach speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. These supersonic winds drive enormous storms across the planet. When Voyager 2 flew past in 1989, it observed the Great Dark Spot, an Earth-sized anticyclonic storm. By the time Hubble observed Neptune a few years later, the Great Dark Spot had vanished entirely, replaced by new storms. Neptune's atmosphere is violently dynamic, constantly reshaping itself. Neptune has at least 14 known moons. The largest, Triton, is one of the solar system's most intriguing worlds. Triton orbits Neptune backward, in the opposite direction to the planet's rotation. This retrograde orbit strongly suggests Triton wasn't formed alongside Neptune, but was captured from the Kuiper Belt, making it a dwarf planet that got too close and was pulled into orbit. Triton is geologically active despite surface temperatures of minus 235 degrees Celsius, one of the coldest places in the solar system. Nitrogen geysers erupt from its surface, shooting dark material into the thin atmosphere. Triton's orbit is also slowly decaying. Tidal forces are gradually pulling it closer to Neptune. In a few billion years, Triton will either crash into Neptune or be torn apart to form a spectacular ring system. Only one spacecraft has visited the ice giants, Voyager 2, in 1986 and 1989. The data from those brief flybys remains our primary source of information, but plans are underway for new missions, possibly launching in the 2030s. Uranus and Neptune, the distant ice giants, remain among the solar system's least understood worlds, cold, mysterious, and waiting to reveal their secrets. Beyond the orbit of Neptune lies a realm of ice and darkness, a vast region where the sun is just a bright star among many. Here, in the frozen outskirts of the solar system, small worlds drift in long, slow orbits, remnants of the planetary formation process that never coalesced into planets. This region, known as the Kuiper Belt, begins at about 30 astronomical units from the Sun and extends to roughly 50 astronomical units. It's similar to the asteroid belt, but far larger and more massive, containing countless icy bodies and at least 5 recognized dwarf planets. Pluto, once considered the 9th planet, was reclassified as a dwarf planet in 2006. It orbits the Sun at an average distance of about 39 astronomical units, taking 248 Earth years to complete one orbit. Pluto is small, about 2,077 kilometers in diameter, smaller than Earth's moon. Its surface is a complex landscape of nitrogen ice plains, towering mountains of water ice, and vast regions of reddish material thought to be organic compounds created by chemical reactions in Pluto's thin atmosphere. In 2015, NASA's New Horizons spacecraft flew past Pluto, returning the first close-up images of this distant world. The images revealed a stunning, geologically active surface, with features like Sputnik Planitia, a smooth, heart-shaped plain of frozen nitrogen, and towering ice mountains as high as the Rockies. Pluto has 5 known moons. The largest, Charon, is so large relative to Pluto that the two are sometimes considered a binary dwarf planet system. Pluto and Charon orbit around a point in space between them, called the barycenter. Other dwarf planets in the Kuiper Belt include Haumea, Makemake, and Eris. Haumea is an elongated, egg-shaped world that spins incredibly fast, completing one rotation in just 4 hours. It has 2 small moons and a ring system, the first ring system discovered around a dwarf planet. Makemake is reddish-brown, likely covered in methane ice, and has at least 1 moon. Eris is one of the largest known dwarf planets, nearly the same size as Pluto. Its discovery in 2005 was one of the events that led to the reclassification of Pluto. The Kuiper Belt is also the source of many short-period comets, comets with orbital periods of less than 200 years. These comets originate in the Kuiper Belt and are occasionally perturbed by gravitational interactions with Neptune, sending them into the inner solar system. As they approach the Sun, the heat causes their ices to sublimate, creating a glowing coma and long tails of gas and dust that stretch for millions of kilometers. In 2019, New Horizons flew past another Kuiper Belt object, Arrokoth, a small, reddish world shaped like a snowman. Arrokoth is made of 2 lobes gently joined together, suggesting it formed from a low-speed collision of smaller bodies early in the solar system's history. It's one of the most pristine objects ever studied, largely unchanged since its formation 4.6 billion years ago. Beyond the Kuiper Belt lies the Oort cloud, a vast spherical shell of icy bodies that surrounds the entire solar system. The Oort cloud begins at about 2,000 astronomical units from the Sun and extends to as far as 100,000 astronomical units, nearly a quarter of the way to the nearest star. It's thought to contain trillions of comets, though we've never directly observed the Oort cloud. Its existence is inferred from the orbits of long-period comets, which arrive from all directions rather than along the plane of the solar system. Long-period comets can take thousands or even millions of years to complete a single orbit. They spend most of their time in the distant, frozen Oort cloud, where they are barely influenced by the Sun's gravity. Occasionally, gravitational perturbations from passing stars or the tidal forces of the Milky Way nudge an Oort cloud comet toward the inner solar system. As it falls inward, the comet accelerates, and when it nears the Sun, it heats up, developing a glowing coma and spectacular tails. The Oort cloud is thought to have formed from icy planetesimals ejected from the inner solar system by the gravitational influence of the giant planets, particularly Jupiter and Neptune. These objects were flung outward into distant orbits, where they remain to this day. The Oort cloud represents the solar system's most distant boundary, a frozen reservoir of ancient material that holds clues to the solar system's formation and evolution. The outer reaches are cold, dark, and quiet, but they are also full of ancient history, preserved in ice and stone. These distant worlds and clouds of comets remind us that the solar system is not just the bright, warm planets near the sun. It extends far into the darkness, reaching toward the stars. At the very edge of the sun's influence lies the heliosphere, a vast bubble carved out of the interstellar medium by the solar wind. The solar wind is a stream of charged particles, mostly electrons and protons, that flows outward from the sun in all directions at speeds of about 400 kilometers per second. It carries with it the sun's magnetic field, creating a protective bubble around the solar system. This bubble, the heliosphere, shields the planets from much of the galactic cosmic radiation that permeates interstellar space. The heliosphere extends far beyond the orbit of Pluto. At about 80 to 100 astronomical units from the sun, the solar wind slows abruptly as it encounters the pressure of the interstellar medium. This boundary is called the termination shock. Beyond the termination shock lies the heliosheath, a turbulent region where the solar wind slows and begins to turn back toward the sun. The outer edge of the heliosheath is the heliopause, the true boundary of the solar system. At the heliopause, the pressure of the solar wind balances the pressure of the interstellar medium, and beyond it lies interstellar space. Only 5 spacecraft have traveled far enough to cross the termination shock, and only 2 have crossed the heliopause, Voyager 1 and Voyager 2. Launched in 1977, the twin Voyager spacecraft were designed to study the outer planets. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, sending back stunning images and invaluable data. Voyager 1 visited Jupiter and Saturn before heading toward the edge of the solar system. Both spacecraft are still operational, more than 47 years after launch, though their power supplies are slowly fading. Voyager 1 crossed the heliopause in August 2012 at a distance of about 122 astronomical units from the Sun. It detected a sudden increase in the density of the interstellar plasma and a drop in the intensity of solar particles. Voyager 2 crossed the heliopause in November 2018 at about 119 astronomical units, in a different direction from Voyager 1. The data from both spacecraft revealed that the heliopause is not uniform. Its shape and location shift in response to changes in solar activity and the pressure of the interstellar medium. Beyond the heliopause, the Voyagers are now in interstellar space, the region between stars. They continue to send back data about the interstellar medium, measuring its density, temperature, and magnetic field. The signals from the Voyagers take over 22 hours to reach Earth, traveling at the speed of light. Despite their distance, they remain humanity's most distant emissaries, carrying golden records with sounds and images from Earth, a message from humanity to the cosmos. The heliosphere's shape is thought to resemble a comet, with a rounded nose facing the direction of the sun's motion through the galaxy, and a long tail streaming behind. However, observations from spacecraft like the Interstellar Boundary Explorer, IBEX, and data from the Voyagers suggest that the heliosphere's shape is more complex than initially thought. It may be influenced by the sun's magnetic field, the solar cycle, and the structure of the local interstellar medium. The heliosphere also breathes. During periods of high solar activity, the solar wind is stronger, pushing the heliopause farther out. During solar minimum, the solar wind weakens, and the heliopause contracts. This pulsing occurs over an 11-year solar cycle, causing the boundary of the solar system to shift by billions of kilometers. Interstellar space is not empty. It's filled with a thin gas of hydrogen and helium, dust particles, and magnetic fields. Cosmic rays, high-energy particles from distant stars and supernovae, also stream through the interstellar medium. The heliosphere acts as a partial shield against these cosmic rays. But as the Voyagers ventured beyond the heliopause, they detected a significant increase in cosmic ray intensity. Even farther out, beyond the Oort cloud, at distances of several light-years, the sun's gravitational influence fades entirely. Here, the solar system truly ends, and the space between stars begins. The nearest star, Proxima Centauri, is about 4.24 light-years away. At current speeds, it would take the Voyagers over 70,000 years to reach it. The edge of the solar system is not a sharp line, but a gradual transition from the sun's domain to the realm of the galaxy. It's a boundary defined by pressure, magnetism, and the fading influence of a star. And though the Voyagers have crossed it, they remain, in a sense, part of the solar system, carrying with them the legacy of a small blue planet orbiting an ordinary star. And so we've drifted from the sun's blazing core to the frozen silence of the Oort cloud, from Io's volcanic fury to Europa's hidden ocean, from Jupiter's ancient storm to Saturn's hexagonal mystery. We've crossed 100 facts, visited 8 planets and hundreds of moons, and traveled billions of kilometers through space, all while you remained perfectly still. But here's the final revelation, the one that changes everything. The solar system you just learned about doesn't really exist anymore, not the way I described it. By the time light from the sun reaches Neptune, about 4 hours, Neptune has already moved. When we look at the planets, we're seeing where they were, not where they are. We're observing the past, watching a cosmic ballet that's already moved on to its next formation. And there's something else. Remember how we started? You're traveling at 828,000 kilometers per hour around the galaxy. But that's not the whole story. The Milky Way itself is moving through space at over 2 million kilometers per hour, rushing toward a gravitational anomaly called the Great Attractor. And the Great Attractor is moving too, pulled by even larger structures in the cosmic web. You are not standing still. You have never stood still. Since the moment you were born, you've been hurtling through space on multiple trajectories simultaneously. Earth's rotation, its orbit around the sun's orbit around the galaxy, and the galaxy's motion through the universe. You've traveled trillions of kilometers and will never, ever pass through the same point in space twice. The solar system is ancient, 4.6 billion years old, but it's not finished. Jupiter's moons continue grinding through their tidal dances. Phobos spirals closer to Mars. Triton falls toward Neptune. The sun slowly brightens, growing about 10% more luminous every billion years. In 1 billion years, this increased brightness will evaporate Earth's oceans. In 5 billion years, the sun will begin its transformation into a red giant. But even as the solar system ages, we're discovering it anew. When your grandparents were young, we thought Pluto was the 9th planet and the solar system ended there. We didn't know about the Kuiper Belt. We'd never seen Jupiter's moons up close. We didn't know Europa had an ocean, or that Enceladus had geysers. We hadn't confirmed a single planet around another star. Today, we've discovered over 5,000 exoplanets, worlds orbiting other suns. Some are hot, Jupiters, gaseous giants, orbiting their stars in mere days. Others are super-Earths, rocky worlds larger than our own. A few orbit in the habitable zones of their stars, where conditions might allow liquid water. The universe, it turns out, is full of solar systems, each one different, each one strange. Our solar system isn't special in the universe. It's one of billions. But it's special to us. It's home. It's where life found a foothold and evolved into minds capable of wondering about Jupiter's storms and Neptune's winds. It's where beings made of stardust learned to build spacecraft and send them beyond the heliopause, carrying messages to an unknown future. 2 Voyager spacecraft, launched in 1977, are now in interstellar space, over 22 light hours away. They've outlived their expected lifespans by decades. Their plutonium power sources are fading, but they continue transmitting data from beyond the edge of the solar system. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star in the constellation Camelopardalis. The spacecraft will be long dead by then, a silent artifact drifting through the dark. But it will carry humanity's message. We existed, we wondered, we reached out. You are made of atoms forged in dying stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces and scattered across space in supernova explosions billions of years ago. You are not separate from the solar system. You are part of it. You are the solar system contemplating itself. Tonight, as you drift into sleep, the solar system continues its ancient dance. Planets orbit. Moons revolve. Comets fall through darkness. And somewhere, far beyond Neptune, the Voyagers keep flying, carrying our stories into the endless night. If this journey helped you unwind or sparked your curiosity, please consider subscribing. There are more explorations waiting, more mysteries, more wonders, more gentle drifts through the cosmos. For now, let your thoughts settle. Let your breathing slow. Let your body rest on this small blue world, spinning through space at nearly 1,000,000 kilometers per hour, while you remain perfectly, peacefully still. Good night, traveler. Sleep well among the stars.